Okay, now it's 11. So everyone's here for Orgo 1, right? Or Orgo 2 and preparing for your ACS. So this practice exam that I'm going to be going over, you can find it on ucfstudyunion.wordpress.com. You just click on the chemistry tab. I don't know why I made the H capital. And then you just, go to your class code. So this review can be found there. I have this, and I also have something called Review of Reagents. It's a whole reagent list that you'll see here. It basically has almost, if not all, of your Orgo 1 reagents, as well as some helpful tables. So I'll give you a book, such as this one that tells you when to use, E1, E2, SN1, SN2. That could all be found in that Review of Reagents link on that WordPress site listed right here. So I would definitely recommend checking that out because that will be big for your ACS. Or just your final in general, depending on what professor you have. Also, this is going to be a little different than typical SARC sessions in that it's going to be a little bit more lecture style. So I'll make it as interactive as possible, but it is going to have to be a little bit lecture style because we have so much material to get through. But I will have like a Q&A section at the end. I'll try to save time for that so we could go back to whatever you guys have questions on. But of course, if something isn't clear, feel free to raise your hand, shout it out, and I'll be asking you guys questions throughout the time. So when you're studying for your exams, I just put here the most important rules to this course. So negative things go to positive things. So when you're doing your mechanisms, even if you don't remember what a reagent does, if you keep charges in mind, you'll know to draw your arrow from nucleophile to electrophile, right? Always count your carbons. That could save you a lot of time. Remember that OH is a bad leaving group. Be careful for hydride and methyl shifts. Don't jump into a certain reaction without evaluating if you could have something more stable. And of course, if you're feeling really overwhelmed by your final, just study a little bit each day. Chemistry takes practice. It doesn't come naturally. I had to put a lot of work into the class to do well, so just study a little bit each day, or a lot. So question number 1, write the condensed formula for the following molecule. Not only is this big for Orgo 1, but to prepare you when you get into Orgo 2, you'll be given a condensed formula, have to transform it into line bond, do a whole reaction, and then your answer will have to be back in the condensed formula. So you're going to have to know to convert very quickly in between line bond and condensed. So let's get started. We always start from left to right. So from the left, we have CH3. This carbon is CH, right? We have 1 hydrogen. Now, how do we write branches? We put it in parentheses, right? CH3, that's our branch, that's our methyl. Down here is a CH. We have a branch of a bromine. Now we're going to this carbon, CH. Whoa, I can't write an H. And then CH3, 2, because we have 2 methyls. Does that make sense? So CH3, CH, we got our branch of a methyl up here, CH3, CH, branch of our bromine, CH, and then we have 2 CH3s, so 2 methyls over here. Does everyone feel okay with that? Yeah? Perfect. All right. So now let's jump into acid base. So I don't know if you could see my meme here, but that's Michael Ketone. So with acid base, we want to complete the following reaction and indicate which side equilibrium will favor and why. So what's our first step with acid base reactions? We want to decide what's our acid and what's our base. So look at these 2 reactions. What's your acid? It may be a little unclear at first, right? Because we see that our ketone here, it has double bonds, it has carbons, that typically makes something acidic. Whereas our water, we know that water can function as both an acid and a base. So this could be kind of tricky. How do we decide? Well, what's the definition of an acid? Yeah, perfect. So acid is a proton donor. What's the only one here that can donate a proton? The water, right? So the water can give up its proton. This molecule, the ketone here, it can't give up its protons because it's covalently bonded to the carbons, right? So it's not going to want to easily give up. So what we're going to do is, our hydrogen is partial positive, right? Because our oxygen is partial negative. The oxygen is pulling the electrons away from the hydrogen, making a partial positive. If we go to our ketone, the oxygen is partial negative because it's electronegative. So negative things go to positive things. That was the important, rule that I had on this other sheet. Negative things go to positive things. So our base, we go from our negative thing, which is the oxygen, and draw our arrow to the positive thing, which is our hydrogen. And we end up getting a structure that looks like this, right? I talked to the organic chemistry 2 professors, like Dr. Fraser, and he tells me to emphasize with you guys arrow pushing mechanisms, because when you get into Orgo 2, if you draw your arrow the wrong way, it'll be like major points off on your exam. So do make sure, I know it's a multiple choice to ACS, but when you're doing these mechanisms, make sure you're going negative thing to positive thing, not positive to negative, right? So this is going to be plus OH minus. So this was our base, this was our acid. This is our conjugate base or conjugate acid? Conjugate acid, perfect. And so this is our conjugate base. Now we want to decide which side equilibrium favors and why. So which side is equilibrium going to favor? Well, so this is something that confuses a lot of students. So you're going to favor the weaker acid or weaker base. So you want to favor the weak side because the weak side is more stable. So the weak side is to the left, right? So equilibrium favors reverse reaction. So you could hear it worded as reverse reaction, or you could hear it just as reactants, right? They could word it either way. Your reverse reaction or your reactants. Why is it going to favor your reactants? We have OH right here. OH is the strongest base you can have. So you're always going to go to the side opposite your strong base in this case, right? Yes? Yeah, so OH, it's when you're dealing with solutions in water here, OH is the strongest base you can have, and so we're always going to go opposite to that side. Yeah. Yeah, exactly. Yeah, perfect. Another reason is we compare our bases. We see that the ketone doesn't have a charge, right? So base to base, our ketone doesn't have a charge, but our OH does. If we compare our acids, water doesn't have a charge, but our conjugate acid does. So the ones with no charge are more stable. So we're going to favor the reverse reaction due to charge. Hey, Damani. You guys feel okay about that one? Yeah? Perfect. So now question 3. This is like a typical ACS question you can get. Identify the most acidic proton among those labeled. So labeled as in the ones that are circled. So what's more acidic, this one or these ones? The one to the left? Right, so it will be the one to the left because this you can hydrogen bond, right? Well, you can hydrogen bond with either one, but nitrogen is more basic than oxygen, so this is going to be able to hydrogen bond, and that's going to make this the more acidic proton. It could give up this proton more easily than the nitrogen can. So more acidic. Does that one make sense? You could definitely, I don't know what's on your ACS, but I would definitely like expect something like that, labeling the more acidic proton. Yeah? Oh, so this one's more acidic because it can hydrogen bond and the alcohol can like easily give up that proton. Your nitrogen is more basic than oxygen, so that's why this one is going to be able to give it up. And this is kind of a similar situation here. Can you guys see that one okay? I'll like zoom in a little bit. So choose the most acidic green proton. When I printed this, it didn't come out in color, but basically look for the proton. So we have 3 protons here. We have one here and one here, right? So this is an alkane, this is our benzene ring, and this is an alkyne. So which structure has the more acidic protons? The alkyne, perfect. And why is that? That's due to sp, right? So when we're looking at acidity, I can't spell, acidity, we have that sp is higher than sp2 is higher than sp3. Our alkane is sp3, right? This is sp2, this is sp. So you're going to see when you take like orgo-2 that you're going to be able to do reactions with your benzene ring also, but your sp, your triple bonds are always going to be higher in acidity. I should zoom out a little bit. Does that make sense? Oops, this guy is more acidic. There we go. You guys feel okay with that one? We go on to number 5. Yeah? Perfect. So number 5, which of the following has the highest boiling point and why? Yeah, perfect. The one that can hydrogen bond, which is this one right here, right? So this structure due to H bonding. What do we also know about boiling point? How is branching related to boiling point? Branching is inversely related to, I'll just put BP because I'm lazy, boiling point. So branching is inversely related to boiling point. So we know these aren't going to have a high boiling point, especially this one because it has that big branch right there. So these are not going to have high boiling points. This one's able to hydrogen bond, so we know that's going to be higher than this one. You guys feel okay about that? Yeah? Perfect. Let me know if I'm going too fast, by the way. Typically, I get through chapters 1 through 5 in about 15 minutes so that we can go full into like synthesis. Do you have more copies? I don't, but it is on the site, on the WordPress site. Did you have a question? The lower, yeah. So over here, when I say like branching is inversely related, that means that like more branching leads to a lower boiling point. Yeah, that's a good question. Mm-hmm. Okay. I'm gonna flip the page here. And for everyone that walked in, you can find this practice exam at this site here, ucfstudyunion.wordpress.com. Okay. Draw the Newman projection from the following molecule. This one's fun. It is a throwback from like exam 1, right? So we have our circle. The stuff that's connected to the dot, that's going to be what's right in front, right? So we're looking from this direction. That means that our dot is going to be what's connected to this carbon right here. What's connected to the outer circle, that's going to be what's all the way back here. So first, I like to start out with what's in the plane, because what's in the plane is either going to point straight up or straight down. So our hydrogen, it's in the plane and it's pointing up, right? Just because the picture shows it's pointing up. So we're going to put our hydrogen right up there. Our chlorine, it looks like it's pointing up a little bit, right? And it's on a wedge. So it's going to go up, and is it going to go to the left or to the right? To the right, right? So if you're looking from the left, your wedges are coming out of the paper. So if you look that way and you have something coming out of the paper, that's going to be to your right, right? Oh wait, did I say left? I meant right if I said left. So that's going to be to your right. Does that make sense? So if you're looking in this direction and you're coming out of the paper, you're going to your right, right? What about your methyl? It's pointing down, and is it going to the left or to the right? It's on a dash. It's going to the left, right? Because dashes, if you're going this way, it's going into the paper. So if you're going this way and into the paper, that's going to the left. So that's your CH3. So now we'll do the outer circle. Our hydrogen is in the plane, and it looks like it's sloping down a little bit, right? So we could put this hydrogen going straight down. What about our dash with the bromine? Where's that guy going? To the left, and is it up or down? Up, right? So up and to the left, perfect. So we're going this way, we're going up, and it's going into the page. So if you're going into the page, you're going left, right? I should say correct instead of right. So now we have our OH that's on a wedge. So if we're looking from this direction and we're coming out of the paper, we're going to the right. So down and to the right. You guys feel okay about that one? Yeah? Perfect. Okay. And also, what conformation did I draw just now? Yeah, gauche, perfect. So this is gauche because they're like a nice distance apart. It would be eclipse if they were all like really close together and overlapping, right? So eclipse is if your molecules are really close together and they're unstable, they're wanting to repel each other. So if you're asked about stability, your most stable is, well, your middle stability is gauche, right? Your least stable is eclipse. And what's your most stable called? Anti, perfect. What's anti? That's when your heavy groups are opposite to each other, right? So I would have to have my alcohol opposite to my chlorine, because chlorine is the heavy group. So we're looking at what's attached to the middle opposed to what's attached to the outside circle. So alcohol is the heavy group on the outside, chlorine is the heavy group on the inside. So this opposed to that, that's anti. Yeah? Perfect. So anti over gauche over eclipse. You guys feel okay about that one, and we get into some enantiomers and stuff? Yeah? Perfect. Let me make this closer. Is that too dark? Can everyone see that? That's okay? So we want to label the following as either the same compound, diastereomer, enantiomer, or mesocompound. And as we go through these questions, we'll define what each of those mean. So with this structure right here, how do we decide if it's an enantiomer or not? That's when its conformation changes, right, from S to R or R to S. So first, for us to even know if it changes from S to R or R to S, what do we have to know? We have to know that it's chiral, right? So what is the definition of chirality? So that's when you have a carbon connected to 4 different groups. In this case, we have, oh, I should zoom in. In this case, we have our bromine That's one group connected to this carbon. We have a methyl, we have an ethyl, and we have a hydrogen, right? So that's 4 different groups. That means this compound is chiral. So now we can label the conformation. What gets priority number 1? The bromine, perfect. So bromine is priority number 1. What gets priority number 2? The left or the right? So some say left, some say right. Let's see how we decide. So this is a methyl, right? So this is a carbon with 3 hydrogens, CHHH. This is a carbon with 2 hydrogens. So we go down on this side. So carbon, hydrogen, hydrogen. We ran out of hydrogen now. This one goes to another hydrogen on the left. Now we have to branch out over here. This is carbon, hydrogen, hydrogen, hydrogen. Now our tiebreaker is carbon against a carbon against a hydrogen. What wins? Carbon, perfect. So the right side gets priority number 2. And then our left side gets priority number 3. We know we have a hydrogen there, right? But hydrogen is dirt to us. It's always number 4. So we're going this direction. Is that clockwise or counterclockwise? That's clockwise, right? Perfect. So is that R or S? Right. So because it's going clockwise, it's R, but our hydrogen is on a wedge, right? So because our hydrogen is on a wedge, we don't like that. So we're going to flip it from R to S. Perfect. And then this one we already labeled. It would just be R. We don't flip it, right? Because it's the same compound. It's just our hydrogen is on a dash, like how we need it to be, right? So we would have 1, 2, 3. That's R. Another way that I learned is that you see how it's clockwise. If you get confused between what's clockwise and counterclockwise in R and S, with R you're going to the right, right? So you're literally turning to the right. Whereas with S, you're going to be turning to the left, counterclockwise. For Orgo 2, I took Dr. Fraser, and a way that he explained it was when you're going right, that's righteous, and when you're going left, you know how in the old days it was like left-handers are evil? So S is for sinister, so for the left. So that's a way to remember it, because I always used to confuse them. So for A, these are enantiomers, because our conformation changed from S to R. So these are enantiomers. Let me zoom out. Enantiomers. There we go. You guys feel okay about that? Okay. Another way that we can see enantiomers, is if you go from like R to S, S to R, or you could go from RR to SS, or SS to RR, conformation. So let's say you had more than one chiral center. If they're both R and they flip to both S, you have an enantiomer. Or like if they're both S and they flip to Rs, you have an enantiomer. And that's going to be important because when we get to meso compounds, it's not always going to be so easy to tell if you're an enantiomer or a meso compound. So we'll compare that now. All right. So question B, we have this structure right here. I'm going to keep it out. So do we have a chiral center? Yes, right? We have a methyl, we have this group, and we have a hydrogen. Does it make sense why this is a chiral center here? Yeah? So what gets priority number 1? Is it over here, the methyl, or down? Down, perfect. So we'll see why. So this is a CH2, right? So this is carbon, hydrogen, hydrogen. This is carbon, hydrogen, hydrogen, hydrogen. But down here, it's a carbon with only one hydrogen, and then immediately we go to another carbon. So this one's winning so far, right? Because carbon beats out hydrogen. So that's 1. Here we have carbon, hydrogen, hydrogen. We're still at a tie, right? So we got to go to our tiebreaker. This could branch out over here. This is carbon, hydrogen, hydrogen. So now we have a carbon up against a hydrogen. What wins? The carbon, perfect. So this gets priority number 2, which means our methyl gets priority number 3, and our hydrogen we don't even write, right? Because our hydrogen is the dirt. We don't need, it's priority 4, last priority. So we're going in this direction, right? So is that R or S? It's R, right? We're turning to the right. It's clockwise. So that is R. Perfect. Now what about this guy? It's basically the same thing but flipped, right? So this gets priority number 1, down here gets priority number 2, and our methyl gets priority number 3. So now we're going this way. Is that R or S? That's S, perfect. So we're going to the left, right? Sinister. So we have RS here. What about this one? It's the same structure, so we could just flip what we had. So now this is going to be S, and this is going to be R. Does that make sense? So you just take what you had and you flip it. Does that confuse? Does anyone have questions on flipping it? I just want to make sure I'm not going too fast. That makes sense while you're flipping it? Okay, perfect. So this one is SR. So when you go from RS to SR, what are you? You're a meso compound, right? So meso is when you go from RS to SR, or of course, you know, you could go from SR to RS. Why is this? Well, remember that meso compounds, they're optically inactive, right? They're optically inactive, so they're canceling each other out. So your R is canceling out your S is canceling out your R. So you could get ACS questions referring to which one is optically inactive. Well, that's your meso compound, right? Or, you know, you can identify your meso compound by doing, you know, RS to SR. Does that kind of make sense? Yeah? Perfect. So remember, an enantiomer is this guy, RR to SS. Meso is RS to SR. So now we have C. So what's going on with C? We see that we have this carbon right here is chiral, right? I should zoom in, I'm sorry. This carbon is chiral, right? Because we have a methyl, a bromine, a hydrogen, and then this big group over here. This carbon is also chiral because it has this big group over here, this methyl, this big group over here, and it has the hydrogen. And then this carbon is chiral because it has a chlorine, it has a methyl, and then it has this big group over here, right? So all 3 of these carbons are chiral. Do we have to go and do R and S for this one? You can if you wanted to, but just by looking at it, we see that these are going to be the same conformation, right? This bromine and bromine. Methyl and methyl are going to be the same configuration, but this chlorine is going to flip. So if your chlorine is the only thing that flips, what are you going to be? Diastereomer, perfect. So let's zoom out and we'll define diastereomer. So this one was meso, this one is diastereomer. You could also hear it pronounced as or written as diastereoisomer, either way. Diastereo. I'm positive that I'm probably spelling this wrong, but that's okay. So diastereomer is when you change the configuration of you know, like greater than or equal to 1 chiral centers, but you can't change them all. Because if you change all of them, if you flipped all of them, what are you going to be? You're going to be an enantiomer. Yeah, perfect. So diastereomer, we could, if I zoom in again here, we changed the chlorine. Whoa, what happened? So here we changed the chlorine, we could have also changed our methyl, right? So we could have our chlorine as a dash and our methyl as a dash, but as long as those bromines stay the same, you're still a diastereomer. So you could change one, you could change two, but you can't change all of them. If you change all of them, you're an enantiomer. Does that make sense? Yeah, perfect. So now we're going to go to D. So what about D? They're the same, right? So why is it the same and not a meso compound? Yeah, so they're mirror images of each other. So if you take this molecule and you like flip it like a pancake, it's going to look like this, right? Or like if you walk behind it, this is what you're going to see. So this is the same compound. Now, if we look back at our meso compound, though, you could flip it like upside, right, and it'll be the same thing, but that's not what we want. For meso compounds, you have to go from RS to SR, or SR to RS. So meso compounds are commonly confused with same compounds. So just be careful with that. Yeah? All right. What was it? Yeah. Yeah, they would be. Exactly. Yes? The enantiomer? How would we change this one into an enantiomer? Oh, so if we wanted to, I'll zoom out. So if we wanted to change this into an enantiomer, then you would flip it. So you could, it was a dash, you can make it into a wedge. Perfect. Okay. So now we're on the last question of chapters 1 through 5, and we'll get into substitution. So we're making good time. So draw the chair conformation of the following structure in its most stable conformation. So we need cis-2-ethyl 1-methyl-cyclohexane. So well, I mean, the name of this should be 1-ethyl 2-methyl, right? But either way is fine. So if your name, it should be this should be a 1-ethyl 2-methyl, right? Because E should come before the methyl, but you know, it'll get drawn the same way regardless. So if we do the chair conformation, oh yeah, it's a quality chair. Whoa. If we do that chair conformation, we want an ethyl. So how do we make it cis? You need to have one axial and one equatorial for it to be cis. So I'll do my ethyl as axial, and then I'll do my methyl as equatorial. So that's one way that you could draw it. So the ethyl, I made it axial because you're pointing up, and equatorial, you're doing like the equator, right? Side, you know, horizontal. Is this your most stable conformation? Perfect. So this is an option that you could draw, but this is not your most stable conformation. Your most stable conformation is going to be with your heaviest group, equatorial. Oops, I'm sorry. I made the equatorial. Whoa. Whoa. There we go. So if you have axial equatorial, then you're going to be cis. If you had equatorial equatorial or axial axial, you're going to be trans, right? So this is the most stable. So on your ACS or whatever exam you're taking, they could give you this structure and this one. But your most stable conformation is the one with the heaviest group as equatorial. Okay? Any questions? No? Yes? Yeah. So if we wanted to make it trans, it would be, it would have to be like axial, axial, or, that's an ugly chair, or equatorial, equatorial. Could I? Oh yeah, so you can make carbon 1 wherever. I just did it here. But yeah, you could do carbon 1 wherever on the chair. Yeah. As long as, you know, if it's 1, 2, you just have to make it 1 and 2. So I could have put carbon 1 here and carbon 2 here. I just put it, you know, here. Basically, your professor will hate you if you put it in the middle, because that's just annoying. So, but yeah, you could see it like that. So did you guys feel okay with chapters 1 through 5? Yeah? Perfect. So you guys ready to get into some substitution? Okay. Oh wait, I flipped it. Okay, like I said, for these substitution and elimination, Markovnikov, like all this stuff we're gonna do, I can only do so much with you guys. I can only get through so many reagents, and we'll get through the concept of how to get through these. But if you want a full reagent list, you could go to the SARC WordPress site, and I have this review of reagents. That's gonna give you basically all of your Orgo 1 reagents. If I'm missing some, you know, don't blame me. But this has like a lot of them, if not all. I also have solvents, how to tell if you have protic, polar protic, and I have a little table here showing when to decide if you're E1, E2, and we'll do that during the session here, but you guys have all of this also in your review of reagents sheet that I made for you guys, okay? So, question number 9. Complete the following reaction and indicate if they proceed by SN1 or SN2. So let's do this one. We'll call this A because I didn't label it. Is this going to be SN1 or SN2? So there's a little tricky guy here, right? So what's going to happen? We know that this is a strong nucleophile, right? Because when you have sodium or potassium with a halogen, you're going to be a strong nucleophile. And what do strong nucleophiles favor? They do favor SN2, right? But can we do SN2 here? No, right? Because it's tertiary. And we can never do SN2 on a tertiary structure. So what do? Our chlorine is our leaving group, right? You want to identify your leaving group. Your halogens are always your leaving group. Or, you know, whatever's a good leaving group. You're never going to have a methyl, an ethyl, any of this carbon stuff as your leaving group, okay? Halogens are really good. So this is a strong nucleophile. This is your leaving group. So SN2, is that 1 step or 2 step? 2 step, perfect. So we're going to have our chlorine as the leaving group. 1, 2, 3. And now we have a carbocation right here. We always have a carbocation intermediate when we're doing SN1 mechanisms. So now that our chlorine left and we have a carbocation, what do we have to be careful for? Yeah, so we have to be careful that we can't do hydride or methyl shifts. In this case, we can't do it, right? Because wherever we move our carbocation, it's not going to be any more stable. But always when you have E1 or SN1, be careful. Because you may have to do it. Yeah, whenever you have SN1 or E1, be careful for hydride or methyl shifts. In this case, we're doing SN1, but you know. So now we could come back with our iodine, and we just attack. Now, when you're dealing with configurations and SN1, what are we going to do with the dashes and wedges? Well, so this one's going to stay the same, right? This guy stays the same. But these are going to be a racemic mixture, and you want to know that word for your ACS. So you're going to have this. You're going to have your iodine. Oops, I drew a hydrogen. That should be an iodine. Plus your iodine will now be on a wedge, and your methyl on a dash, right? And this is called what again? Yeah. I don't know how to pronounce it. I know how to spell it, though. Surprisingly, I know how to spell it. So this is a racemic mixture. So SN1 make racemic mixtures. You have racemic mixtures, whereas SN2, what do you have? You have inversion of configuration, right? SN1 racemic, SN2 inversion of configuration. So now let's go to B. What's this guy going to be? Well, so we have a secondary structure and we have a strong nucleophile, right? So that's indicating, that's pointing towards SN2, right? But what's this guy? A solvent. And what kind of solvent? It's a polar protic solvent, right? Protic because we have a proton. So this is a polar protic solvent. So that's going to force our reaction to be SN1. So even though we have a strong nucleophile, we have a secondary structure, our polar protic solvent is going to force this to be SN1. Now what if this chlorine was primary instead of secondary? It would have to be SN2 because SN1 can never be primary. It can never react on a primary structure. But because it's secondary, we can do SN1. Perfect. So our chlorine is going to leave. For SN1, we always have our carbocation intermediate, right? So we have our carbocation right there. We have our propyl. And do I just come back with my iodine and attack? No, what happens? A hydride shift, right? Because we have a secondary carbocation right here. We can make it tertiary because what's more stable, secondary or tertiary carbocation? Tertiary. So we're going to do a hydride shift. We have our little hydrogen friend right there. It's going to jump down, stabilize. Right? So now this is neutral, but this has a carbocation because we lost a hydrogen. So we have a tertiary carbocation. Now we can come back. I'm sorry, this desk is like in an awkward place, so I'm having to like bend my paper. So now we could come back with our iodine and attack. When we attack, this is SN1, so again, we're going to have that racemic mixture. Iodine plus, put the plus down here. Oop, you can't even see what I'm drawing. Okay, so we have our propyl on a wedge, our iodine on a dash, and then our propyl on a dash and our iodine on a wedge because this is SN1 and we have that racemic mixture. Yep. All right. Okay. Predict the product and note whether the following proceeds via E1 or E2. And we want to note the Zeitz-7-Hoffman products. So we have a lot of stuff going on over here. So first, let's identify what's happening. With elimination reactions, we want to eliminate, we want to pick off a proton, form a pi bond, and a leaving group is going to leave, right? E2 happens all in one step. E1 is multi-step, just like SN1 was multi-step and SN2 was one step. Over here, what do we have to be careful with? We have a ring structure. So whatever proton we pick off has to be anti to the leaving group. That's because you have a cyclic structure. So I'll put it up here. With cyclic structures, your hydrogen must be anti, or you may have heard it phrased as trans, to the leaving group. Right? So that'll help us determine what our leaving group is. If we look at this chlorine, it's on a dash. Now let's look at the adjacent carbons. This carbon doesn't have any protons to pick off, right? So we can't do anything there. This carbon, it has a hydrogen, right? But it's on a dash. Is that trans or anti to the chlorine? No, right? So chlorine, that's not going to be our guy. I mean, you could take one from up here, but that's not going to be a major product. So we have 3 hydrogens up here, right? So you could have a product right there, picking off one of these hydrogens and forming a double bond. We'll make that product too, it's just not going to be a major product. Now if we look for our iodine, this carbon right here, it doesn't have any hydrogens, but this one, it has one on a dash and one on a wedge, right? So we could pick off the hydrogen that's on a wedge. So I'm going to go with my NaOMe. I'm going to pick off that proton, form a double bond, and at the same time my iodine leaves, because this is an E1 mechanism, right? I'm sorry, an E2 mechanism. How did I know that this was E2? Well, so the reagent is in the strong nucleophile, strong base category, and it's a secondary structure, right? So if we go to that table that I gave you guys of the reagent list, if we're looking at strong nucleophile, strong base, that's this category, right? Because all you have is an OMe, an oxygen with a methyl. So an oxygen with a methyl is going to be in this category, the O with the R, negative. Secondary structure, you do your E2, right? So we're going to form a product that looks like 1, 2, 3. Like that, right? So this is one product you could form. And then we identified the other product, picking off one of the hydrogens on this methyl group, right, and forming a double bond right there. So another thing we could do is we have our OMe, pick off one of those protons, form a double bond. Does this look messy? Do you guys see what I'm doing? I know it looks messy, but we're picking off the proton on this methyl, forming a double bond, and this chlorine is going to leave. And we're going to get a product that looks like that. Yeah? What did you say, Josh? What was that? I'm sorry. Oh, I'm sorry. Yeah, right there. Yeah, there we go. Thank you. Yeah, so our methyl was there. I just didn't. I made a mistake. I get negative 20 points on my exam. Okay. So now we have these two structures. Do you guys have any questions on how we got these two structures before we do Zaitsev and Hoffman? No? Okay. So between these two, what's our Zaitsev and what's our Hoffman product? Yeah, perfect. First one is Zaitsev. And this is Hoffman. Does Zaitsev mean major? Most of the time, right? Zaitsev means more substituted product, whereas Hoffman means less substituted product. Is your Zaitsev always your major product? What's your exception? Bulky bases, perfect. So with bulky bases, your Hoffman product is your major product, but we don't have a bulky base here, so our Zaitsev, our more substituted product, is our major product. And how did we know it was more substituted? We look at the double bond. The double bond is in the middle of the molecule here, so we look at the carbons that the double bond's connected to. This guy's connected to a carbon here, this guy's connected to carbon here. We look at this one, double bond here. The bottom part's connected to these two carbons. The top isn't connected to anything. So this one is more substituted for that reason. Yeah?
Is there a third compound? Can't you do elimination to the right?
Oh, doing picking off a hydrogen here? Yeah, you could do that too. Yeah, so Luis even found another one. So another product that we can have, it wouldn't be our major or minor though, but you could have another product. Would be, this is our chlorine, this is our propyl, 1, 2, 3, double bond there. Right, so that's another one that you could do because this propyl has two hydrogens, so we could pick off a proton from the propyl, form a double bond, and have that iodine leave. This wouldn't be a major or minor product, but it is another product that you can have. Yeah?
Could you also do substitution as well?
Yeah, you could do substitution also, but your E2, yeah, exactly. Yeah, perfect. Did that one make sense? Yeah, perfect. So now let's go to B. So we have tert butoxide. So we're told to do E1 or E2, but can you even do substitution here? No, right? Tert butoxide can't do substitution with tertiary structures. That's just, you know, I mean, the question told us E1, E2 anyway, but tert butoxide, you just can't do it with tertiary structures. So we identify our leaving group with it, which is chlorine. We have tert butoxide. He looks like that. It has a potassium connected to it, right? So TBUO, that's tert butoxide, but the K, that just means that's with potassium. Does it make a difference if it's potassium, sodium, etc.? No, right? You could have any metal there. You could have potassium, sodium, whatever. It's still tert butoxide. Because whenever you're bonded to a group 1A element, it's just going to dissociate and it'll form tert butoxide here. So what's going to happen is we look for our adjacent hydrogens, right? So this carbon, it has 2 protons here, 2 protons here. The structure is symmetrical, so we could pick either side, right? So I'm just going to put them here. And we also have hydrogens on this methyl group. We have 3 hydrogens here. So we could start with these. I'm going to pick off a proton, form my double bond, and chlorine is going to leave. And we're going to get a structure that looks like we still have our methyl, our double bond, and a bunch of methyls out here. So that's one structure we can get, right? Is this E1 or E2? It's E2, right? Tert butoxide is going to favor E2 reactions because it's in that strong nucleophile strong base category. So these were both E2. What's another product that we could get? Well, we could have picked off this proton up here. So we could have picked off the proton, formed a double bond, chlorine leaves, and we get that structure, right? So now between these two products, what's your Zaitsev and what's your Hoffman? Yeah, perfect. So Zaitsev is our left. Hoffman is your right. What's your major product? Hoffman, perfect. Is your major product and this is your minor. And again, your Hoffman in this case is your major because terbutoxide is a bulky base. So a bulky base is your Hoffman is your major. You guys have any questions on that one? No? Perfect. All right. So now we'll go into naming the following molecule. I'll zoom in. Oop, I zoomed the wrong way. Whoa. Why did it zoom out? Stop it. Okay. So we want to name the following molecule. Some rules that we know for naming. So like when you're going into a naming question, what I would do first is identify your parent chain. Identify substituents. I would ask, is there chirality? And then we want to put the name in alphabetical order. Alphabetical order. Right? So what's our parent chain? Well, we have 1, 2, 3, 4, 5, 6, 7 carbons is our longest chain. It's an alkane, right? So 7 carbons, it's an alkane, so we call that heptane. So I'm just going to, like, on the side, create a list of what we have. So we have a heptane, right? We have a heptane. What substituents do we have? We have methyls, we have bromine. We have to number them, right? So which side is carbon number 1 and which side is carbon number 2? So some say carbon 1 is to the left, some say to the right. How do we know? Well, it's the one that gets to the substituent first. So 1, 2, if we get to carbon 2 here, we have a methyl. We have to go 1, 2, 3 on the right side to get to a substituent. So even though bromine is typically higher in priority than methyls, you get to a substituent first going from the left opposed to the right. So that's why this is going to be carbon 1, 2, 3, 4, 5, 6, 7, right? So on carbon 2, we have a methyl, and on carbon 3, we have 2 methyls. So 2, 3, 3, trimethyl. So 1, 2, 3, 4, 5. And on carbon number 5, we have a bromo. Can we just put it together and name it right there? We have chiral centers, right? So let's look for our chiral center. Is this guy a chiral center? You guys were bamboozled. So this carbon right here, you have a methyl here, a methyl here. So they're both methyls, so they're not chiral, right? So be careful with that. For chirality, by definition, you need 4 different groups connected to the carbon, right? So don't let the ACS bamboozle you. If you have 2 of the same group, you're not chiral. So this guy's not chiral. What about this guy? Is he chiral? No, right? They're both methyls. What about this guy? Yeah, right? So we have an ethyl out here, a whole group over here, a bromine over here, and then we have our hydrogen. So this guy is chiral. So now we have to assign configuration to put it in our name. So what gets priority number 1? The bromine. The bromine is higher in priority than all this carbon stuff. So now to get priority number 2, let's list out what we have. We have carbon, hydrogen, hydrogen. Over here we have carbon, hydrogen, hydrogen. That's tied, right? We can't decide yet. So now we have to go to the next side over. Carbon, hydrogen, hydrogen, hydrogen is on here. Over here, we have a carbon with no hydrogen. It just goes to another carbon and on. So what wins? The left, right? So carbon versus carbon, carbon versus hydrogen, the carbon wins. So that gets priority 2, which means priority number 3 is this way, right? Because hydrogen is always priority 4, right? That's, like I always say, your hydrogen is dirt. Like, we don't even draw it. So now we go this way. Is that R or S? R, right? We're going to the right. That's clockwise. So our bromine, I'm just going to put it over here so we remember, R5, right? So now we got all our chiral centers. We could put the name together. All right. So we would name this in alphabetical order. When we do it in alphabetical order, do we take the tri into consideration? No, right? We go by the M in methyl. In this case, it doesn't matter because your bromine is first in the alphabet anyway, because of the B. But in case you had other substituents on here, you would go by the B versus the M, not the B versus the T, right? We don't take into consideration mono, di, tri, etc. I mean, we don't do mono anyway, but you know what I mean. So this is R, we put it in parenthesis, 5, bromo, 2, 3, 3, oops, that should be a dash, trimethyl heptane. That's our answer. Any questions on that one? Yes? Yeah. Oh, yeah. So let's say one of our methyls had a chiral center. We would still indicate the R or S at the very beginning of the name. So hypothetically, let's say that on carbon number 2, you had an S. Just hypothetically, it would then be 2S, 5R. And then your whole name, like 5 bromo, etc. Does that make sense? Yes. Oh, well, we would. So the reason that we didn't here was because bromo was at the very front anyway. But let's say that, you know, let's say bromine didn't have a chiral center, but it was the methyl. We would have to put 5. You know, or let's say it was on carbon 2 with the methyl, it would be like 2S and then 5 bromo, etc., right? Yeah. Did that kind of make sense? Yeah, perfect. Yeah. No question? Okay. All right. So now we're going to do some synthesis. This makes me happy. So this tends to stress people out, so I gave you like a nice meme with a dog with a little watermelon on its head, a cat with an orange on its head. So this makes me very happy. So synthesis tends to stress people out, but hopefully you grow to love it. Like I said, the important rules of chemistry, especially with synthesis, negative things go to positive things. And remember all of this also. When I was in Orgo 2, there was an exam that I went into that I was like, I have no idea what the answer to this is. But I knew that negative things go to positive things, so I ended up getting the question right. So if you know this, I would emphasize this over and over again. You can get to your answer if you know that negative things go to positive things. So I have another meme for you there. Compare and contrast concentrated and dilute H2SO4 in the following reaction. So one of them I have with dilute H2SO4, and one of them I have with concentrated H2SO4. So let me just turn. I'll turn to that page. through what mechanism are we completing this? Oh, you can't see it. Through what mechanism are we completing this? This is Markovnikov, right? Because it's dilute. So some of you said E1. E1 is if you have concentrated H2SO4, whereas if you have dilute H2SO4, you're going through a Markovnikov addition reaction. So let's do it. The way that I do this, I'm not sure how you learn, but the way that I do this is the only difference between dilute H2SO4 and concentrate H2SO4 is their concentration of acid. Acid is what? H3O+, right? So when I do this mechanism, I put H3O+. Now with addition reactions, what do we want to do? We want to get rid of a pi bond to pick off a hydrogen, form a carbocation, and come in and stabilize that carbocation, right? So what we're going to do is, this is Markovnikov. Markovnikov means what? Yeah, perfect. So Markovnikov means that we're going to add something to the more substituted area, and what we're adding is not going to be the hydrogen. So this double bond is going to pick off a proton, and we're going to get our carbocation where? Here or here? This one, right? The more substituted area. This is our carbocation. Just in case you were like curious about it, our hydrogen went here to the end. This is where we have our carbocation because it doesn't have enough bonds. So now that we got rid of a hydrogen, we're just left with H2O, right? We had H3O+, we lost the hydrogen, now we only have 2 hydrogens on that molecule. So we have H2O. We go in, negative things go to positive things, right? This oxygen is partial negative. Oh, look, we got a carbocation right there. Now they're happy together. So you have this structure. Do we have any formal charges?
Yeah.
What is it?
Oxygen is positive.
Yeah, perfect. The oxygen has a positive charge because an oxygen with 3 bonds is positive 1. An oxygen with 1 bond is what charge?
Negative.
Yeah, so if you have an oxygen with 1 bond, it's -1. If you have an oxygen with 3 bonds, it's +1. And now we don't like things that are unstable, right? This has a charge, so it's unstable. So we come back with another water, and we just deprotonate. And we get that. Whoa, you couldn't see what I wrote. There. Is that okay with everyone? Yeah? So we put our carbocation on the more substituted area. Negative things go to positive things. Our negative oxygen went to our positive carbocation. We added it on. And then this had a positive charge on it, so we just came back with water. We deprotonated, and we ended up with an alcohol there instead of a water. Yeah? So now let's contrast that with B. So we have concentrated H2SO4. What mechanism is this going to be? This is E1, right? There's an E1 reaction. So you can't do E1 in many situations, but when you have concentrated H2SO4 or when you have water, you could do you could do E1 mechanisms. So concentrated H2SO4 is kind of another one that makes OH a good leaving group, because OH, what do we know? It's a very, very bad leaving group, right? It'll never leave. But we could come in, we said that we could rewrite H2SO4 as H3O+. So negative things go to positive things. This partial negative oxygen can come pick off a proton. It'll become water, and now it's a great leaving group, right? Water is a great leaving group. So this can leave. You'll get your carbocation intermediate, and you can form your double bond. Now, why did we have a carbocation intermediate? It's E1, right? E1 is multi-step. So just like with SN1, with E1, you have to have a carbocation intermediate. So now we'll come back in and, you know, we'll just have our our water. So where do we have our protons we could pick off? We have 3 of them here, and we have 2 of them here. So we're going to form a double bond in both areas, right? So I'm going to come around, pick off that guy. We're going to get a product that looks like that. And we're going to get a product that we could pick off this proton and form that double bond. We'll get something that looks like that. Yeah? So let's call this A and this B. What's your major product? B, perfect, because B is what? Zaitsev, right? That's more substituted, whereas A, that's less substituted. So that's your Hoffman or your minor product. Well, not or, it's just less substituted. You guys feel okay about that one? Let's see, our time. Okay, we're good with time. Yeah? Perfect. Can I flip the page? Okay, perfect. All right. Get out your ID. So now we're going to go over reagents that make alcohol a good leaving group. So I have all of these on the reagent sheet, like I said, but we could go over what does what. So all of these are going to make OH a good leaving group, but we have to know what to do with them. And I'll tell you, these are all going to stick with you in Orgo 2. So every single reagent we're going over during this session, you want to remember for Orgo 2. There are some Orgo 2 students here that can tell you that. So, POCl3, what does that guy do? It's going to make OH a good leaving group, but what is it going to do? Substitution or elimination? Close. Well, you said substitution and that was close, so it's elimination, right? My microphone is like stuck to my hair. This hurts. Okay, everything is okay. So now, so what POCl3 is going to do is going to get rid of the OH and just going to put a double bond somewhere. It doesn't matter where we put the double bond. No, right? It's symmetrical. So I'm just going to put it there. So POCl3 with pyridine. Pyridine is just a base. Like it's just there. But POCl3 is just going to get rid of that OH and put a double bond. Yeah? What about for B? PBr3, what does that do? I don't know if you guys could see it. Substitution, perfect. So this is going to create, you just take off that OH and put on a Br. That's all you do. So this one was substitution. This one was elimination. What about C? This guy looks weird, right? But let's go step by step. What is step 1? It's TSCl with pyridine. What is that going to do? It's going to switch out the OH with an OTS, right? So we're going to redraw it. OTS. We have, I don't know why I made this look so complicated right there. So that's step 1, right? You just take out your OH and put on an OTS. So we went from a very bad leaving group being OH to OTS. What is OTS? It's like the best leaving group you can have, right? So now we can come in with NaOMe. This is where we have to think a little bit. What are we going to do? Substitution or elimination? So you could do substitution, you could do elimination, but you're going to favor You could do both. Like, all products are going to form, but your major product is going to be with elimination. Because NaOMe, with a secondary structure that's taking out the secondary structure, is going to favor E2. So this is going to be an E2 reaction that takes place now. NaOMe. But we could draw the substitution product also if you guys want. So NaOMe, there's going to be E2 and what? So we could do E2 and what? SN2, right? So it could be E2 and SN2, but E2 is going to be favored. So we could have a product picking off a proton right here, right? So we could go with our O, pick off that proton, form a double bond, and our OTS leaves, and we can get we will get something like that, right? So this is just the methyl that was down here. I just put it up like this. So that's one elimination product we can get. Another one we could get is picking off the protons down here, right? Because we're looking at this carbon. It's connected over here, and over here are the adjacent ones. So another product we could get is picking off this proton, forming that double bond, and the OTS leaves, and we could get, something that looks like, I want to make sure I draw it right, like that. So that's another product you could get. These are your E2. If we wanted to do SN2, all we would do is OTS leaves, NaOMe comes in and attacks that carbon that it's attached to, right? So our SN2 product would be OMe with that methyl, and then our ethyl. I feel like this microphone went off. Can anyone hear me still? Yes? Okay. So this is our SN2 product, and these are our E2 products. What's our major product? 1, 2, or 3? 1, perfect, because that's the most substituted product, right? Whereas this would be our minor product. So this would be Zaitsev or Hoffman? Zaitsev, perfect. So this is Zaitsev, this is Hoffman. If I write it, it might make things look confusing, but Zaitsev. Oh, like pointing up instead of down? So that's just typically how it would be drawn, like doing the zigzags. Oh, I thought that was you. I'm sorry. Yeah, it would be like doing it with zigzags. Also, I put it up here. Yeah, that's just like the standard of how it's drawn. Like going in line with the zigzags. Yeah. Does that make sense? Yeah, so it was pointing down before. I just pointed it up so that we would keep with that zigzag kind of thing. But you could draw it in either way. Oh, that's okay. Do you guys want me to change my batteries? Can everyone hear me? Do you want me to change batteries? You can hear, okay. Otherwise I could recharge. Okay. So perform the following reaction and indicate if they proceed via Markovnikov, anti-Markov, Syn, or anti. When I talk loud, I squeak, so let me know if this gets annoying, and I'll change my batteries. So step 1, what is that? Yeah, perfect. And that's going to be what? That's going to be Syn Addition, right? This is Syn Addition. H2O2, that indicates anti-Markovnikov, right? So this is anti-Markov. So because we have Syn Addition and anti-Markov, we're going to add on what's next to the H2O2. So what's next to the H2O2 is this NaOH, right? So we're going to add on this reagent to the less substituted area, because anti-Markovnikov means you're adding to the less substituted area, right? Markovnikov means you're adding to the more substituted area. So we're going to end up with, we're going to get rid of that double bond, and we're going to have a methyl and an OH. So I'll draw that first, and then we can do we can make it syn or anti. This is what your product's going to look like. But now we need to make it Syn Addition. How do we do that? Perfect. So when we make this syn, we would need something like this as a dash and this as a wedge, or this as a wedge and this as a dash. Now syn means the same. Why are these different? Yeah, so it's syn in regard to what you're adding on. So we got rid of a double bond. We did that by adding on a hydrogen from this structure. So we added on a hydrogen and we added on an OH. That means that our hydrogen is over here, and it has to be the same as the other thing we added on. So these two are the same, and we have a hydrogen here that's on a dash also. So that's syn. Syn in regard to what you're adding on. Yeah? Perfect. Also something that I should note up here, all of your reagents making OH a good leaving group, they're all going to be substitution except for POCl3 and concentrated H2SO4. So instead of memorizing like, oh, this one's substitution, elimination, POCl3 and concentrated H2SO4 are going to be your only two that are elimination for reagents making OH a good leaving group. That's how I like to remember it, because I'm not. H2SO4, yeah. Concentrated H2SO4, and that's an E1 mechanism. So now, for question 14, what is this going to go by? Markovnikov, anti-Markovnikov, Syn, anti-addition. So MCPBA, I know in this class, a lot of you were like taught to memorize that MCPBA with H3O, that makes a trans diol, right? But what's really going to happen is step 1, we're going to form an epoxide. Step 2, we're going to break open that epoxide and form a trans diol. So step 1, you're going to have your epoxide. That's what MCPBA does. Now we're going to come in with H3O+. I'll just put H2O. And we're going to attack one side, open up that epoxide. Yeah, making the little house. Open up that epoxide, and we have an oxygen with a negative charge there, and a water over here. What did I do just now? Was that oxidation or reduction? To know that's oxidation. So just be careful when you're doing oxidation and reduction that you're able to define which reagent is which. So now we have this oxygen with a negative charge, and we have this oxygen here. Does it have a formal charge? Yeah. What is it? Positive 1, right? Perfect. So positive 1. So some of you may have been taught to come back with water, deprotonate this, come back with water again, and protonate this. But honestly, what you can do is a proton transfer. So just negative things go to positive things, right? This is your negative thing, this is your positive thing. Just pick off that proton. And you get 2 OHs. Are we done there? No, we have to make it trans, right? So this makes a trans diol, meaning they have to be opposite to each other, right? So this will be a dash, and this will be a wedge. Or, you know, you could have put your wedge here and your dash here, it doesn't matter. Does that one make sense? Yeah? Perfect. Yeah? So now we'll flip. All right. No, stop zooming out. Okay. KMNO4 with NaOH cold. Be careful for those in Orgo 2. KMNO4 does something different for you now, right? But for Orgo 1 purposes, KMNO4 with NaOH that's cold, what is it going to make? Syn diol, perfect. And what is this, oxidation or reduction? Oxidation, right? We're adding diol, we're adding a lot of oxygen on there. So this one is going to be Syn diol, so your OHs are going to, you know, you could have it like this, or of course, you know, you could have them both on dashes. Yeah? Either of those products. Now for D, Lindlar's catalyst. So we'll compare and contrast H2 with Lindlar's catalyst versus H2 with PT, a metal catalyst. So what does Lindlar's catalyst do to alkynes? It makes it cis, right? Yeah, perfect. What's special about that? It doesn't want to be cis, right? What's more stable, cis or trans? Trans, right? So we need a catalyst to force this to be cis because it wants to be trans otherwise. So oh, I'm missing a carbon. Count your carbons, people. Let me just look at it, otherwise I'm going to be going crazy here. So this is going to look like that, right? Cis meaning your heavy groups are pointing the same direction, right? Another way you could look at it is your hydrogens are going the same direction. So you have hydrogen here and hydrogen here. So cis means your light groups are going the same direction, your heavy groups are going the same direction, down, up, you know. So Lindlar's catalyst, in summary, goes from an alkyne to a cis alkene. Any of these reactions you could be asked to put in words on the ACS also. So just know like how to put it in words, like alkyne to cis alkene. What about this reagent? H2 with PT. So we're going to go from an alkyne all the way to an alkane, right? That's what H2 with a metal catalyst does. So we're going to have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5 carbons. And on this carbon, we have a branch. So it's going to look like this, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. So we go from an alkyne all the way to an alkane. Side note, what if you did this? What if you did a ketone with H2 with PT? What is that going to be? You make it an alcohol. Perfect. So if we're going from a ketone to an OH, what is this, oxidation or reduction? Reduction, perfect. So this reagent is reduction. Because we reduced our bonds to oxygen. All right. Here's a good question. Predict potential reagents for the following reaction. So what is this reaction called? Yeah, perfect. So this is enol keto tautomerization. You have a few reagents you can choose from, but what are some that we know we can use? We could do H2SO4 with HgSO4, right? Or we can do, so you could have this going on, or you could have like 9 BBN with H2O2 and NaOH. Or you can have BH3 THF with H2O2 and NaOH. So any of these three will bring you through enol keto tautomerization. Did we want to do the mechanism for it? Sure. Okay. That'll give us, we'll do the mechanism for this, and then we'll get into our nice 8-step synthesis problem. So let me just get a piece of scratch paper. Here we go. So we'll just do it with, we'll do this one to here with, I'll just choose H2SO4 with HgSO4. So what we're going to do is this, we can rewrite it, right, as H3O+. Our pi bond is going to pick off a proton. And we're going to get 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3. We're going to get a pi bond right there. And this is going to make it into, where is our, we'll have a carbocation. Oh, you guys can't see anything I'm doing. Whoa. Right, so this pi bond picked off a proton. We got a carbocation. Now we can come back with water, because we had H3O+. We lost the hydrogen, now we have water. Well, now this oxygen can attack over here, and we'll get this guy, right? This has a positive charge. We could come back with water again, because it's in a solution of water, and stabilize that positive charge, right? Because it's not happy right now. And we get that. What is this step called? What are we called right now? This is an enol, right? En, double bond, all, alcohol. Enol. That is an enol. So now what can we do? Well, we can come back with our H3O+. I know there's a long mechanism, so that's why I was like, do you guys want to see it? We could come back with our H3O+. That pi bond, again, picks off your hydrogen, and you get this with a positive charge in the middle. Now we can do resonance. So an oxygen with a positive charge is more stable than a carbon with a positive charge. So we're going to want to stabilize that carbocation. and get this. And now, as the very last step, we can come back with our water, pick off that proton, and end with our keto, right? This is a keto. This is an enol. We went from an enol to a keto. Why did we even want to go from an enol to a keto? Well, ketos are more stable than enols. Even like when you guys do biochemistry, ketos are going to be the major product in your body, whereas enols is just like, get out of here, right? So, did this mechanism kind of make sense? We're basically just doing charges, negative to positive. Which step? Here? Oh, so, oh, here? Oh, so here we did resonance. So an oxygen with a positive charge, like over here, is going to be more stable than a carbocation. Carbons, they don't like to have charges on them. The oxygen can handle that charge much better. So we're going to do resonance, stabilize that carbocation, and get with an oxygen that has a positive charge. And then we just come back with our water to stabilize it. Yeah? Perfect. And the ACS kind of likes enol keto tautomerization for some reason, but there you go. Good to know. So now we could go to our 8-step synthesis. Yeah. Okay. So we're probably going to need scratch paper again for this one. I'll keep it on me. Okay, so this is a good problem because we'll be able to define each and every reagent as we go along. So lithium aluminum hydride, this is a whole exam. Basically in Orgo 2, you have lithium aluminum hydride and NaBH4. And a lot of students that took, that used to come to my sessions in the spring and the summer, they ended up getting like really well on that exam because I showed them how to do the mechanism. Well, and they worked hard, so. But also, it was a review. So lithium aluminum hydride, you're going to take your ketone and you're going to make it into an alcohol. So what's going to happen? Well, your lithium, you have a metal here, that group 1A, 2A metal, whatever it's in, it's a metal. So it's going to easily dissociate from the AlH4. So I'm just going to put Al over here. Whoa. We have an aluminum with 4 hydrogens around it. Now aluminum, it has a positive charge, right? Because it's a metal. Metals always have positive charges. So since this is a positive charge, it's not going to be bonded to other positive things. It's going to be bonded to negative things. So these hydrogens all have a partial negative charge on them. So we're going to attack, we have to attack something, right? Negative things always go to positive things. So this is our negative thing. This molecule has a positive thing. Well, it's a ketone, right? So this is partial negative. Where's our partial positive? Yeah, the electrophilic carbonyl center, right? So this is our electrophilic carbonyl center. We're going to go with our hydrogen and attack that center right there. By the way, Dr. Hashim and Dr. Fraser know I love them, so if I talk like them, then I'm just joking. So, so this is going to become a secondary alcohol because this is going to do resonance. This is going to have a negative charge, and then it's going to pick up a proton from that water, right? Do you guys want me to draw it step by step? No, either way. So this did resonance. It had a negative charge, and then the oxygen picked off a proton from this water and became a secondary alcohol. Does that make sense? Yeah? So this was reduction, right? Because we went from bonds to oxygen to an alcohol. Now we have an alcohol. We're going to do step 3, tosylate with pyridine. What does that guy do? It makes OH a good leaving group. Perfect. And what are we going to do? Elimination or substitution? Substitution, right? Because when you make OH a good leaving group, your only reagents that do elimination are POCl3 and concentrate H2SO4. So we're going to switch out our OH with OTS. That's step 3. Now we went from a bad leaving group into a really good leaving group. So step 4 is tert butoxide. That's tert butoxide, right? So we're going to want to do an E2 reaction. You could do different types of reactions here, but when you're doing multi-step synthesis, tert butoxide will only do E2. So just keep that in mind. When you're doing multi-step synthesis, tert butoxide will only do E2. So since it's E2, we look for our adjacent available protons. We pick it off, form a double bond, OTS leaves. And we get that. So it looks simple right now, right? So that was step 4. Now we have step 5. Can we do step 5 alone? It has to be paired with 6, right? Because BH3THF, that's Syn Addition. But this H2O2 with NaOH, that's what's going to add on and do anti-Markovnikov, right? So it's step 5 and 6 together, right? So this is anti-Markovnikov H2O2. We're going to add on our OH to the less substituted area. So we're going to get that, right? So we get rid of the double bond, add on our OH. What about step 7? What's going on there? What does that do? Cool. So it's not an aldehyde. So this reagent is going to make it into a carboxylic acid. A shortcut to knowing this is you see this chromium, this Cr with O. When you see those reacting with an alcohol, it's going to make your carboxylic acid. So, you know, you could have sodium, you could have potassium, you could have hydrogen. That's nonsense. You see your Cr and O, it's going to make a carboxylic acid out of your alcohol. So you don't have to memorize the 50 reagents that do the same thing. You could just be like, oh, CRO, carboxylic acid. So that's going to make something that looks like, I don't want to draw this weird. There. It's going to make something that looks like that. And it'll be paired with H2SO4 and H2O. But, you know, like I said, this is the key. Okay, so now that we're in the home stretch, right? We're on step 8. Should I zoom out? Whoa. Now we're on step 8. What does SOCl2 do? Perfect. So this is something that makes OH a good leaving group. We're just going to take out that OH and add on a chlorine. So our final answer will be this guy. Yeah? So we took this 8-step synthesis problem, and it looks really big and really long, but just going step by step, we're able to break it down and get into something that we just went from a ketone to an acyl chloride. And you want to know all of this for Orgo too. So just breaking it down, reduction makes OH a good leaving group. E2, Syn Addition, anti-Markovnikov. What was this? Reduction or oxidation? Oxidation. And then this just made OH a good leaving group. So on your ACS or whatever exam you're taking, final exam, be able to, define all of them for what they are. See its true colors. All right, you got it. Oh, so for part A, For part A above, what are some other reagents in step 7 you could use to accomplish the same product? So like I said, step 7, you could have had potassium with this stuff, you could have had a hydrogen with this stuff, you could have had like a CRO just alone. That'll all make that carboxylic acid, right? And that's all on the reagent sheet. What if you want to form an aldehyde instead? So step 7 here, it made a carboxylic acid. What if instead we want to form an aldehyde? What would we use? You know it, John? No? Josh has to know this. So we want to, PCC, perfect. Very important for Orgo 2. So step 7, you have a primary alcohol, you want to make an aldehyde, you use PCC. Very important. I called you out. All right. Does anyone have questions on this? No? Perfect. Yeah, so Damani, this is for Damani, because Damani got it. I guess Damani, I'm more of noob, and this is Damani, I guess. Okay, so how about C? Let me see how much time we have. Okay, we have like 15 minutes, so I'm gonna go Speedy Gonzalez here. So excess NaNH2 followed by an ethyl attached to an iodine. What is the first step? That's gonna be E2, right? So base only, this is a base only reagent. NaNH2, and what's your other base only reagent that'll do the exact same thing? Perfect. So you could have this, or you could have NaH, exact same thing they do. They're in that base only category of the reagent list I gave you guys. So just to save time, this is gonna form an alkyne, right? I mean, if you guys want me to do the mechanism, I can, but it's just gonna form an alkyne, right? So we're gonna have something that looks like 1, 2, 3, 4, 5. The alkyne, we have to draw it straight, right? So 1, 2, 3, 4, 5. That's step 1. Are we done there with step 1? No. Can we go straight to step 2? No, because how do we react things? Negative things go to positive things, right? We don't have a negative thing here to react with a positive thing. There's an ethyl with an iodine. We can't do anything with that. So what do we have to do? Yeah, perfect. We have to deprotonate. And this is a covalent bond, right? An alkyne with a hydrogen right here. This hydrogen is covalently bonded to the carbon. That's a strong bond, a covalent bond, but it's able to give it up because this is our acidic proton, right? And this is a base-only reagent. So we could give up this proton because it's a very acidic hydrogen. So we come back with our NH2, deprotonate it, and form our carboanion. Carboanion, or I say it in an annoying way. Carboanion. So now we come with step 2. It's an ethyl with an iodine. Now we have a negative thing that could go to a positive thing, right? This iodine, we just kick that guy out. We say thank you next to that iodine, and we just add on that ethyl. And that's our final product. Yeah? Perfect. So with excess, you can keep reacting and reacting with your base-only reagent. sometimes you stop here, sometimes you don't. We knew to keep going and make it into a carbonyl because our second step was an electrophile. If your second step was not an electrophile, if it was like, you know, water or something, then we would do other things. But because you had an electrophile, we had to deprotonate and keep going, right? What about this one? So this is a base-only reagent, but we're going to deprotonate the acidic proton, right? This is the proton that could be most easily given up, not all of this covalent stuff. So you could form other products by picking off the protons on these carbons, but your acidic proton is the one bonded to this OH, well, bonded to the oxygen. That's the one that can be given up most easily. So we come with our negatively charged hydrogen, pick off that hydrogen, and we get an oxygen with a negative charge. Now, negative things go to positive things, right? Negative thing. This is a negative thing. It's electronegative, so it's pulling the electrons away from this carbon right here. It's causing this carbon to be partial positive, right? So this negative thing is going to attack your partial positive, and it's going to kick off that iodine, and you're going to get an epoxide. You're going to get that. That one makes sense? Yeah? Everyone's feeling okay? All right. So I'm going to flip it. Okay. So now we want to open an epoxide. So because it's steric hindrance, we're going to open the epoxide to the less substituted area, at the less substituted area. So this oxygen is going to attack. We open it up, and we get 2, 3, 4, 1, 2, 3, 4. We have that and that, right? So this oxygen came over here. So I had 1, 2, 3, 4 carbons. 1, 2, that's where we have our well, not isopropyl, but this guy. And then this is where the oxygen went. Here is where the OH attacked. And now we just come with water and protonate it. And that's your answer. How much time? So we have 8 minutes left. We could get into spectroscopy and radical reactions now if you guys like. Yeah? So that's in celebration of being done with synthesis. I like that one. So just look at its face. So many of you feel like this about spectroscopy. A lot of you guys don't really like it. I know Amar likes it. Some of you are saying, hippity hoppity, get off my property. What do you mean? So Amar likes spectroscopy, but I know a lot of people. Okay. These are some important things to know about spectroscopy. I won't spend too much time on it because you guys have it on the WordPress site, this whole list here. So I know we only have a few minutes, so I don't want to spend time on something that's written out for you already. But these are just some good things to know for spectroscopy. Mass spec, you're identifying molecular weight. IR, you're doing functional groups. NMR, you're doing the carbon-hydrogen framework. That's on the WordPress site for you guys. You want to know your ratios still. So you're on a mass spectrum, you still want to know the ratio with chlorine and bromine and all of that. That bromine is a 1-to-1 ratio, whereas chlorine is a 3-to-1, and be able to identify it on a graph. So with these 5 minutes left, did you guys want to go like quick through spectroscopy? Did you have like, or did you want to do like radical reactions? Radicals? Okay, perfect. So I'm going to mark where we left off so that I can I'll post the answers to what we didn't do at spectroscopy, okay? And if we have time, because this will take like 2 seconds, we could do some spectroscopy. Okay. So can you guys see that? So it's this long carbon chain, an oxygen with a chlorine reacting with NBS. This is a reagent you want to know not only for your ACS, but you want to know it for Orgo too. I don't know if you guys could see the structure, but basically what NBS is going to do is we're going to look for where is our double bond. So our double bond is right here with this guy, right? Here's our double bond. We're going to go to the adjacent carbon. So this isn't a carbon, this is a chlorine. We're going to go to the adjacent carbon and add on a bromine. I'll zoom out, right? So this is where our double bond was. We go to our adjacent carbon and just add on a bromine. That's NBS. And it could be paired with heat or whatever, it'll do that. If it asks you to put it in words, you're adding your bromine to allylic carbon. Okay? Now what about this one? Now, you can do radical reactions like this with bromine. You could do it chlorine paired with light. But they're going to react a little differently. Bromine is more selective. So bromine, you're going to form it at the more substituted area. So all you're going to do with your product here, I'll zoom out, is you're going to keep the exact same structure, but you're going to add a bromine to the to the more substituted area. So right there. If you had chlorine, let's say this wasn't bromine, but it was chlorine, you could add your chlorine anywhere. Your chlorine isn't selective, it just goes at it, right? So that's the difference between chlorine and bromine. Bromine is more selective. Yeah, chlorine is just gonna yeah. Yeah, so bromine is gonna go to the most substituted area, which is, in the middle right there. A radical mechanism. Let me see if I have it written. I haven't. Let me see. Let's check it out. I don't have one on me. I don't want to draw the wrong thing. But I know it is in the book. I could try. I don't have it on me, but when I put up the answers, I could look at it and put it with the answers. Yeah. Okay. So that's all I have for radicals. I don't know if we have time. We have 2 minutes left. I could do some spec. Let's zoom out. All right. So graph the M+1, and base peak for CH4. So on a mass spectrum, we want to know our y and x axis. Our x axis is MZ, and our y axis is relative abundance. So relative abundance is just how much you have of it in the how much of that molecule you have in your sample, and MZ is just the mass to charge ratio, because your mass is your mass and your Z is your charge, and your Z is going to always be +1. So you're just calculating your mass. So if we're looking for CH4, our M+ peak is going to be the weight of CH4. So on the periodic table, if you guys do a throwback to like Chem 1, carbon has a weight of about 12, right? I know back in Chem 1 you guys did like 12.0 whatever. That's nonsense now. We do 12. So we don't do like the O whatever in these problems. So 12 plus, we have 4 hydrogens, 4 times 1 instead of 1.008, right? That's going to be 16. So our MZ, our mass, is going to be at 16. That's going to be a peak. We're also going to have something called the base peak, and that's going to always go to 100. This is your M plus, and because this is carbon hydrogen, we're going to have an M plus 1 peak. Your M plus 1 is literally your M plus. Your M plus 1 is your M plus, which is 16 plus 1, so it's 17. And this peak is going to be a lot shorter because it's taking into consideration carbon 13. And carbon 13, in regard to relative abundance, carbon 13 is much less abundant than carbon 12. So that's why your M plus is taller. An alternative way you could see this written is that your base peak and M plus both go to 100. So your base peak and your M plus could be the same, but they don't have to be. Yeah? They could be the same, but they don't have to be. It's 101. All right. These, just look at the ratios. That would be that question, like bromine and chlorine. So I'll post that. IR, I don't really have much there. Yeah, memorize. For NMR, how many peaks? Well, know that N plus 1, you're using that for calculating peaks. For calculating peaks in same environment, so for example, our structure here, we use N plus 1. Whoa, why do you keep doing that? We use N plus 1 when we're dealing with HA and HC. And then we do N plus 1 times N plus 1 when we're calculating peaks in different environment, which, you know, for example, is HB, and this is for total peaks. But if we wanted visible peaks, it would be, you know, peaks in different environments, all this, but you're going to use N plus M plus 1 for alkyl halides. So N plus 1, that's when you look at your adjacent carbon and you're calculating the peaks of your, you know, adjacent hydrogens. And they're all in the same environment. So HA, its adjacent hydrogens are all in the same environment. HC, its adjacent hydrogens are all in the same environment. But for HB, if you want the total peaks, you have on this side HA and this side HC. They're in different environments, so for the total peaks, you have to use this. If you want visible peaks, you have to use N plus M plus 1. Yeah. Perfect. So thank you, guys. No problem. Thank you guys for coming.